You kind of stole my first slide, but this is my project on UAV-based sonar, which is for bathymetric monitoring of Roadheath Lake and with the before and after of Hurricane Helene. And so this is going to be formatted in like two different sections, with the first one being our like testing and proving this UAV system to work, and then with the second section we'll be comparing before and after with Hurricane Helene data. And so for the background, you might have a question like, why would you do why try bathymetric monitoring with UAVs? And so we were trying to find different methods of collecting bathymetric monitoring. And as this project was funded by the NCDOT, they were really interested in like this whole side of bridge inspections, as that's pretty important for like understanding. And we're just trying to find alternative methods for bridge inspections for the DOT. And we were trying to use UAVs because they are a very flexible platform that can allow for a lot of different like sensors to be used and work in a wider variety of environments than traditional sonar systems would work for. Like if you're in like a high gradient stream with like really high water velocity, you couldn't get a boat with sonar or like even an ROV there to use it. So that's why we went with the UAV path. And with different sensors, you can capture a bunch of different data with just a couple flights and then use all of that to really get a good look at the scene. And so for our equipment, we use the DJI Matrix 600 Pro. It's a very good like heavy lift drone that is, it's a little old now, but it works very well for our purposes. And so for collecting our sonar data, it's the ECT 400S echo sounder. It's a little bit of a mouthful, but it's a tethered system, so it's going to be hanging from a rope under the drone. And to get these two systems to communicate to each other, we used a platform called the SkyHub, which connects directly like to the inside of the drone, and then the sonar plugs into it. And this is where like all of the data will be logged and stored with the GPS tags from the drone. And so this is what the drone looks like when it's carrying the sonar sensor. The tether is about 2.5 meters long, so it's just hanging below it. And it hangs just below the water surface, and this is what it looks like when it's flying about. For our ground truth collection to validate our data, we just went out in a canoe with a 25-foot rod. There I am holding it. It's a little unwieldy, but so we went around our study site and collected 30 different ground truth points and we used the Trimble DA2 GPS to log all of the tags and record the depth information. And this system worked really well for us because it's a high accuracy, and we used that later. And so as I mentioned earlier, we're located on Roadheath Lake, which is near Morganton, North Carolina, in Burke County. And so the red rectangle is our study site that we surveyed. And for our data collection, we flew the drone twice and went and collected ground truth data with the canoe. So the black dots are our ground truth points we collected, and the first in the red flight line was an automated path. We used the UGCS flight planner for that to program the route and then fly that. And then the other one in orange was flown manually by a professor I work with. And this was just because the reason we didn't fly completely autonomous for the whole system was because being near those bridge footers, it's kind of scary to lose, because if the drone's older, so it doesn't have like obstacle avoidance or anything that would like prevent us from just crashing straight into a bridge footer and then losing a lot of money in the water. So we did it the old-fashioned way and entrusted it all on one person. So for using those points in ArcGIS Pro, I then interpolated it using the kriging method to create like what you're used to seeing for a bathymetric map. And some interesting things about this: we recorded a maximum depth of about 6.5 meters or 21 feet. And to just kind of get a better understanding of this entire area, so this reservoir is flowing to the east or downstream from here. And so this is the downstream section of the bridge. And these little red arrows, I'm not sure if you can see it on the projector, but they are pointing at the expansion joints on the bridge, because directly below all those expansion joints are where the bridge footers are. And so so these are 2 points of potential like scour or erosion. As you can see, those are right between the bridge footers. And so that's just kind of like useful information for like the DOT to be like, oh, there might be potential erosion and scour going on at these footers. And that's something that we would like, that they might be interested in, and maybe send out a dive team to like look at that more. And so using this like generated raster, I overlaid the ground truth points and then extract the raster values to perform an accuracy assessment. And so it's important because it's the interpolated, so it's not the like actual values of that the sonar sensor was collecting, but we got really good results by comparing these two with a R squared of 0.9 and the RMSE of about half a meter. And also because this drone's a little older, it has a vertical error of about half a meter as well. So in my opinion, most of the errors and the reason these like don't perfectly line up is from that vertical error that we could be having, as well as just interpolating, because there's not real data there, that's just what the computer thinks is. So we were really happy with these results, and that really led us to trust in this system. And so just a quick little like processing workflow. I took the drone flight from UGCS and then brought it into a software called HydroMagic. It's for processing sonar data. So you just it's subjective. You'll go through the echograms and you just kind of remove any points that look like error values if there's like random spikes in the deep sections. And so you just clear that stuff and then can export it for use in a program like ArcGIS, which is what I use to do most of my interpolation and processing on this data. And so we use the universal kriging method because our partner, we have on the same grant, there's a partner at Mississippi State that found that the universal kriging worked best for this sort of underwater bathymetric mapping. And so that we just kind of went with that, and looking at all the different results, it looks the most like what you're used to seeing for a bathymetric map. And then using those ground truth points on the raster, I extracted them out to do the accuracy assessment. And then after that, I just generated a couple of those maps as you saw with the inside of ArcGIS. And so that's kind of just the first section of just proving that this whole system works and that we are that we're not getting bad data from it. Because Sonar's been around for a while. We were just wanting to test this particular application of the system. And then after our first collection, which was in August 22nd, 24, Hurricane Helene happened. As I'm sure you all know, it was a really crazy storm to live through. And this is just a 48-hour rainfall map from the National Weather Service. And so I think we're right up here with our study site. So we weren't in the crazy heavy rain that places like Asheville got, but there was still just a ton of water moving through the Catawba River Basin. And so this is a unit stream flow map, also from the Weather Service, that kind of shows where the just crazy amount of water that was moving through these systems at this time. And so it's it might have been as bad as the French Broad or some other areas, but there was a ton of water moving through the system. And just severe storm that we had never really seen before. And so to kind of get a better view of what was going on with the water during Helene, I took the data from the nearest USGS gauge station, which is at the Roadheast Dam, which is about 13 miles downstream. And this is what it looked like, because it's a dammed, controlled river. It is pretty solid at about 10 feet. But during the hurricane, it jumped up in a day, 24-hour span. It went from about 10 feet to 25 and a half feet almost, which is just crazy for a lake to over double in its depth for such a short period of time. And so now that we'd proven that our sonar system worked, this really gave us the opportunity to test and study what such a historic flood event had on the bathymetry of a lake. And so we went out for a second data collection on November 1st. We didn't go immediately after Helene because Watauga was kind of, a disaster zone still. So we were getting things sorted out there. But we used the same drone with the same parameters, the same flight path, and we still flew it manually just because we still didn't trust it. But we just wanted to keep everything as similar as possible for comparison's sake. And then I did the same exact step where I used these points to generate the bathymetric map. And so right off the bat, the maximum depth that we found went from 6.5 meters to 9 meters, which is about 30 feet. And this is a very large increase in like depth, maximum depth for compared to our first collection. And it's just really, yeah, there was just a lot of change that occurred. And so for comparison's sake, I took the first raster, first depth map that I made, and then applied the same symbology, so you can really just look at them to compare the two, how much deeper this channel got. And so some interesting things, like the original, those two sites I pointed out that might be like between the footers that are scour, kind of one of them got much deeper is the river channel. I kind of pointed out. The river channel looked like it went like this way and curved around, then it changed and jumped, and then it's been this way now. So we got a much deeper central section along with some deposition along this bank. And I think that my theory for why there was some deposition on that bank was because of as those floodwaters were receding, because there was a really heavy sediment load in all of this water that just got deposited on that bank as it was receding. And so to kind of like quantify this and get a better look, I created a change detection raster, which is just by subtracting those two previous rasters I created. And it shows the most extreme erosion in red with some deposition in blue. And you can see there was a point that had over 5 meters of erosion between our two studies, which is a lot. That's like over 17 feet of erosion that occurred in probably just a couple days span, which is just really absurd to me that it can change, because it's a lake. You don't expect it to have such severe changes so rapidly. But so the total study area for these rasters is about 5,400 square meters, and that's the point where there was the 5 meters of change. And the erosion went of the 5,400 square meters, over 4,500 of them were areas where erosion occurred, with a total of almost 10,000 cubic meters of eroded sediment and soil during this time. And then on the flip side, there was about 900 meters or square meters of deposition for about 1,000 cubic meters along that bank. And this is just crazy. Going back to that super deep spot of erosion, that was where the river kind of moved a little bit to the south and just started eroding through the bank, which was next to the previous deepest point. And so I think that's why there was such a severe change in maximum depth. And then for, once again, more visualization, I created a 3D representation of the bathymetry. And you'll notice in the background there's a bridge. That was just from some drone ortho photos we took. I generated a 3D mesh with some photogrammetry just to kind of help illustrate where each of those bridge footers are, and just so you can really see how the river channel kind of changed from sloping to the right, but then just kind of sloping in a different pattern and really, really hollowing out that area behind the footers. And so you can see those little cylindrical polygons are showing the deepest point for most of it. And so the deepest point moved a little bit to the south and got over almost 3 meters deeper than the first one. And I think that just having it in this view can really help to illustrate the sorts of changes that occurred, and really, it's just a really valuable way of showing this. And then this is the area that experienced about 5 meters of change. You can see that little bank right there that just kind of really got cut off and got much, much deeper during this flood event. And then so this is, this is just me playing around because I made this it's in the 3D viewer in ArcGIS Online. So this is just me kind of me playing around with it. But I think that this sort of tool to demonstrate and be able to visualize what has occurred underwater is really useful for the policymakers and the people that if you're needing hey, maybe this bridge needs to be repaired, and they can show you this sort of product. I think that can be just incredibly valuable information and can really help connect the because who really knows? Not many people are in the know of fluvial responses to this sort of stuff. I think that these sorts of products are really helpful and are just a very valuable like final product for this sort of thing. And then, yeah, for the final data processing, it like the same beginning, which is like getting the data, processing it, and then interpolating it. But since we now had these two different rasters, I could do a more comparative analysis. And so that was I did the change detection by just subtracting the after raster from the before raster. And then I used the cut fill tool to go and get that's how I got like the deposition and erosion values. And then finally just making the final map for it. And then to get those 3D things, I had to convert the raster into a triangulated irregular network, and then convert that 10 into a 3D polygon, and then add the Z values back to it so we can see what's going on. And then just finally uploading all of that into ArcGIS Online and creating the tool for it. And so to conclude, we found that our UAV-based bathymetry really had just strong correlations with what we measured in site, and it provided accurate, high-resolution data that is at like a much greater level of detail than traditional methods would acquire, as well as the just ability to visualize the bathymetry in 3D with like that bridge we found to be a very useful tool for kind of demonstrating what's going on in this area. As we did run into a couple like, not issues, more so like limitations of our system of not really wanting to crash a lot of money into that bridge. So we had to, so like this can be solved pretty easily with newer drones where like if we have obstacle avoidance, we'd feel a lot safer planning a route like that maybe goes around the footers so we can get a full view of like, oh, what's going on in front of the bridge and just that sort of stuff. But without any of like RTK or just obstacle avoidance, we really didn't want to crash this system. And then there's just some limitations with Sonar itself where it can only have, it's got like minimum depth that it can sound. I think it's, on our sensor, it's about like 1/2 meter or so. So that's pretty shallow, but that still leaves some information going up onto the riverbanks that we don't get. And I think that this sort of thing was, for our research, we were thinking about using structure from motion or like LiDAR to try and, because that can penetrate just a little bit of the water. And if we can get a couple feet of water and then we can go to the sonar sensor for the rest of the data, then we can really get like a holistic view and really just connect those shorelines just all the way down and allow a really full picture of what's going on in the underwater area. And I think that's a just super valuable tool and is our future research direction, hopefully. Thank you all so much. This is a little QR code to that ArcGIS map if y'all are interested, and I can take any questions. Are we doing that?
Yeah, sure. Yeah, thank you for this.
Go for it.
You mentioned this was expensive devices, and I'm sorry I missed the first part of your talk. I'll cover this, but have you thought about using basically a remote control boat?
The reason that we used the UAV system was to try and, because we could like switch to different sensors, so we can go from sonar to like a camera if we want to do photogrammetry. We looked into like ROVs and that sort of stuff, but because our goal, because we're up in Boone, and so we've got a lot of really high gradient streams that are really fast that maybe an ROV just wouldn't be able to map properly. So that's why having the UAV is an advantage.
Have you looked at any other type of lower cost sonar system, or even like using Lawrence or Hummingbird instead of something that you could use ping sonar with?
Mm-hmm.
Lower the cost in general to do the whole workflow.
I think the total system cost was like $20,000, which is for like the sensor, the sky hub, and the drone, which is pretty expensive. But we had one of I can't remember what it was called. We tried using a little for one thing you'd like drop off the side of your boat for like on like a kayak or something to try and see if that kind of data worked. But it just didn't have the beam width on the sonar was too wide to get like the detailed information that we wanted out of it.
Okay.
So, yeah. That answer your question?
Yeah.
Yeah.
Yeah, this is amazing project.
Thank you.
Yeah. And so I
The survey, if we're not going out in a canoe and collecting points, it's like a 20-minute flight and then just processing the data back at the office. Like you just set it up, hook it up, and you can fly it automatically really fast.
Automatically, is the software control them?
Yeah.
So it's pre-planned or it's operated on field?
It is a pre-planned route for the most part. We did end up flying it manually just because we wanted to get close to the bridge footers, but we didn't want to crash it because we didn't know if like maybe there was some like GPS errors or something that would happen. But yeah.
How about the ground truth points? How many you
I-
collected at the first one?
I think it was like 29 points was what the final number, which is in like just throughout that study area. Yeah. Yeah. Oh.
Someone raised their, yeah.
So the elevation data you're getting,
Yes.
is this coming from like RTK module on the drone?
The drone is not RTK. It's just I think it's like a DGPS, so it's got like 3 different ones that it's using, and that's where the elevation data is coming from. But if you had RTK, it would be using that for the elevation data.
So you think there is some room to improve your accuracy?
Oh yeah, because RTK is just a much superior to traditional GPS. We think that would definitely help improve our overall like R squared and RMSE values for, yeah.
Go ahead. That was kind of a follow-up question to that. You discussed your air. I just want to make sure I heard right. 'Cause I work with bathymetric data at the coast, so it's quite shallow as well.
Yeah.
You said it was about a half a meter was your air.
Yes.
Thank you.
Yeah.
I work for Burke County. I'm just curious, why, and I came in a couple minutes late, you may have said so, but why did you choose Lake Roadness?
There was a team that we like. It's a Arit Engineering or something. They're the like NCDOT contractor, and I guess we had gotten. I wasn't there for this decision to choose that site, but I think it was just because we got in contact with them, and we also went out with them when they did their bridge survey, just to kind of compare that.
So it worked out. Good.
Yeah.
Okay.
Any other questions? Let's do have time, I think.
Yeah.
So, yeah, go ahead, please.
Yeah.
How did you ensure that like the water level was the same elevation like pre and post LE?
So I had the USGS gauge data, and they were like, I think 0.3 feet off or something. So it was really close, just because it's a controlled like system. But we also took, when we were out there with the DGPS, we also took like a water level measurement of it and just used that. Yeah.
Did the rate the water flows in the stream impact your sensor's ability to get a vertical line at the bottom?
So this sensor has like all of its on board is it has like I think it can go like up to like 15 degrees or like no maybe 30 degrees in either direction before and like still be able to capture good data because it just is correcting all of that on the fly while it's getting it. Yeah.
I was just going to mention that each USGS gauge has metadata that informs you of the altitude accuracy of the gauge as well as the accuracy of the gauge.
Mhm.
So good call on using that.
Yeah.
Any other questions? No? I have a question for you.
Yeah.
So when you fly the UAV, do you fly right above the water surface or?
Yeah, it's like just above. It's like a couple feet above. That's why it's so scary.
Okay, gotcha.
Yeah.
Okay. No questions?
All
Okay,
right.
and let's thank Stephen.
Thank you.